So now applications of Gauss law. In this, three applications are there in the chapter. The first one is field due to an infinitely long straight uniformly charged wire. Okay, the electric field due to, we can derive the equation for the electric field due to infinitely long straight uniformly charged wire. So we consider here, this is the diagram. So this is the uniformly, we consider here infinitely long, okay, so very long straight uniformly charged wire. So the charges are uniformly distributed here. The charge is Q here. So then here the charge density, linear charge density lambda equals to Q by the length is L. Okay, the length, sorry, it is L. So then here Q equals to lambda into L. So this is equation number 1. Okay, now we consider here, to find the electric field of the long straight infinitely charged wire. So then we can apply the Gauss law. So when apply the Gauss law, we can imagine that, imagine a Gaussian surface that is cylindrical surface. So this is the cylindrical surface. Okay, cylinder. The cylindrical surface length is L. So then here the direction of the electric field, so it is outward direction, in this direction and in this direction. And here the area vector, so in this position ds3 and E is same direction, so it is theta equals 0. So ds1, both end sides, curved sides, so it is ds1, and ds2, it is perpendicular to the electric field. So then from Gauss law, so here pi equals to pi 1, here pi 2 plus pi 3. So different positions, first position, second position and third position. So then pi equals to Q by epsilon naught. So Q equals to lambda L. We can substitute Q equals to lambda L. So pi 1 equals to pi 1 at this position, circle integration of E bar dot ds 1 bar plus circle integration of E bar dot ds 2 bar plus circle integration of E bar dot ds 3 bar equals to Q equals to lambda L by epsilon naught. Okay, here different positions, that equals to circle integration of E ds 1 cos 90 degrees. Okay, the angle between E and ds1 90 degrees plus circle integration of E ds2 cos 90 degrees plus circle integration of E ds3 cos 0 degrees here equals to lambda L by epsilon naught. Cos 90 equals 0, so plus 0 and plus 0 here, cos 90 plus cos 0 equals to 1. So then circle integration of e into ds3 equals to lambda L by epsilon naught. So that implies, so here the so it is implies, so then circle integration of e ds3 equals to lambda L by epsilon naught. So this is equation number 2. So now e is constant, so e circle integration of ds3. Okay, so what is the area of this cylinder is 2 pi r L equals to lambda L by epsilon naught. So here we cancel out the L and L term, so then the equation becomes E equals to lambda by 2 pi epsilon naught into R. So this is equation number 3. So E, the electric field, okay, electric field for infinitely long stated uniformly charged wire E equals to lambda by 2 pi epsilon naught into R. So it is inversely proportional to the distance from the wire to the cylindrical position is inversely proportional to the 1 by R. So then vectorial form, so it is written as E bar equals to lambda by 2 pi epsilon naught R into n cap. So here n cap is unit vector, okay, and again the direction of E is directed outward if lambda is positive. Okay, outward direction from this direction and this direction also. Okay, and inward direction, if lambda is negative. When the lambda is negative, the charge is accumulated on this straight conductor wire is negative charge. So when it is negative charge, lambda is negative, then the electric field direction is inward direction. So when it is positive, so then lambda is positive, the charge is positive, lambda is positive, then the electric field direction is the outward direction from the conductor. So next topic is field due to a uniformly charged infinitely plane sheet of this Gauss law application, second application. So here this is a plane, a charged plane sheet, infinite plane sheet. So it is consist positive charge, the charge is Q. So then we consider the surface charge density sigma equals to Q by S. S is the surface area, so Q equals to sigma into S. Okay, now so here surface area, here we consider the surface area S equals to A, then Q equals to, sorry, it is sigma into A. It is equation number 1. Surface area, so consider A. Now we have to determine the electric field at point P at certain point. For this purpose, construct a Gaussian surface. The Gaussian surface is a cylindrical surface here. The cylindrical surface of this Gaussian surface area is capital A. Then, so it is consist 3 parts here. First part left hand side, and second part right hand side. Third one is at curved surface. The electric field at left hand side and ds bar, okay, surface area is both are the same side. The angle is theta equals 0. At right hand side, this also parallel to each other, so then theta equals 0. At curved surface, the electric field direction and area, surface area direction is perpendicular to each other. So then here we consider here the total flux, total electrical flux, so pi equals to pi 1 plus pi 2 plus pi 3. Okay, so here it is left hand side, it is right hand side, it is curved surface. So then pi equals to circle integration of E dot ds. So it is left side plus circle integration of E bar dot ds bar, it is right side plus circle integration of E bar dot ds bar, it is curved surface. Okay, so pi equals to left hand side E ds. So what is left hand side? It is cos 0 degrees plus right hand side circle integration of E ds cos, it is also 0, plus at curved surface E ds both are perpendicular to each other, it is cos 90 degrees. So that equals to, it is cos 0 equals to 1, so then E circle integration of ds plus E circle integration of ds plus it is 0. Okay, so then pi equals to E into A plus E into A. That implies pi equals to 2E into A. This is equation number 2. Okay, from Gauss law, so pi equals to Q by epsilon naught. So what is Q? So pi equals to sigma A by epsilon naught. So this is equation number 3. So from equation number 2 and 3, so we can write here sigma A by epsilon naught equals to 2 into A. So here A and A gets cancelled. So then the electric field E equals to sigma by 2 epsilon naught. So this is equation number 4. The electric field E equals to sigma by 2 epsilon naught. Sigma is a surface charge density, epsilon naught is a permittivity in free space. Okay, now vectorially it is written as E bar equals to sigma by 2 epsilon naught into n cap. Okay, n cap is a unit vector, so we know that it is unit vector. So then what is the direction of E? So E is directed away from the plate. Okay, the plane sheet. If sigma is positive, when it is positive here, sigma is positive is nothing but sigma equals to q by a. Okay, q by surface area. So q is positive, sigma is positive. Okay, the charge is positive, sigma is positive, E is directed away from the plate and towards the plate, if sigma is negative. When it is negative, the charge is negative, sigma is negative, then the electric field is towards the plate. So here E is the independent of x. X is nothing but here from the center, this is x. Here also it is x. It is independent of x, but it is depend on sigma only, surface charge density. So here the application of Gauss law, third application, field due to uniformly charged spherical cell. So we consider this is the spherical cell. On the spherical cell, positive charges are accumulated. The radius of the spherical cell is capital R. Okay, then here the sigma is the surface charge density. So the surface charge density sigma equals to, so here sigma equals to charge q by area. Okay, surface area. What is the surface area is 4 pi r square. So then q equals to sigma into 4 pi capital R square. So this is equation number 1. So here 3 cases are there. So first case is the electric field at point P outside of the cell, Okay, so here at outside, this is the outside at any point, so this is outside at the P. So when we can find out the electric field at point P. Here the point P, we can imagine that a charged, okay, it is a spherical shape of the Gaussian surface. The Gaussian surface is a spherical shape. It is passes through the point P. At point P, electric field direction and this surface area ds is both are at same direction. It is parallel to each other. Then theta equals 0. So then at a point P outside the cell, the pi equals to circle integration of E bar dot ds bar equals to, so what is the equation? Integration of E ds, so cos 0 degrees, because both are parallel to each other. So then pi equals to E circle integration of ds. So then pi equals to E into, so what is the area of this spherical shape, Gaussian spherical shape? The radius is r square, small r square. So then it is 4 pi r square. Okay, this is equation number 2. According to Gauss law, from Gauss law, so pi equals to q by epsilon naught, or pi equals to sigma, okay, q equals what? Sigma 4 pi r square by epsilon naught. So this is equation number 3. From equation number 2 and 3, so we can write here, so E into 4 pi r square equals to sigma into 4 pi capital R square by epsilon naught. So here both sides 4 pi and 4 pi gets cancelled. So then E equals to we can write here sigma by epsilon naught into, okay, here it is r by small r whole square. So this is equation number 4. So this is the electric field. Electric field E equals to sigma by epsilon naught into r square. So r by r whole square. So vectorially, so it is written as E bar equals to sigma by epsilon naught into r by small r whole square, okay, into n cap. So this is the electric field E bar equals sigma by epsilon naught r by r whole square into n cap. So here n cap is unit vector. This unit vector, the direction of E is outward direction when here sigma is positive. So E is inward direction to the spherical cell. So E is negative. And second one, now electric field at a point P on the surface of the cell. So here the electric field E equals to, we know that 1 by 4 pi epsilon naught. So this is Q by R square. Okay. equation number 1. And what is Q? Q equals to sigma into 4 pi r square. Okay, on the cell. So this is equation number 2. So then electric field E equals to 1 by 4 pi epsilon naught. So it is substitute Q equals to sigma into 4 pi r square and the equation number 1. So then sigma 4 pi r square divided by r square. Okay, here r square gets cancelled, 4 pi gets cancelled. So then electric field E equals to sigma by epsilon naught. Okay, this is equation number 3. Electric field on the cell, okay, surface of the cell, on the surface of the cell at point P equals sigma by epsilon naught. So vectorically, so it is written as E bar equals to sigma by epsilon naught into n cap. N cap is a unit vector. Okay, this is the direction when the sigma is positive. So it is sigma is positive, it is the direction, outward direction. Sigma is negative, the E is direction is the inward direction. Okay, third case, electric field at point P inside. So here third case is inside the spherical shape, inside the spherical cell. So this is third case. So for example, we can, this is a spherical shell. Okay, in this spherical shell the radius is r, capital R. The charge is accumulated on the spherical shell, that is Q, charge Q. Okay, now so the surface charge density sigma. So we can calculate at a point P inside the spherical shell electric field. So then we can construct a Gaussian surface like radius is r. The direction is outward direction, it is also outward direction, ds bar. Okay, so then the electric flux pi equals to, so what is electric flux? Pi equals to circle integration of E bar dot ds bar, that equals to circle integration of E ds cos 0 degrees. So pi equals to E circle integration of ds, that equals to E into 4 pi r square. Okay, so this is equation number 1. From Gauss law, okay, pi equals to charge by epsilon naught. So inside the spherical cell the charge Q equals to 0. So here inside the spherical cell spherical cell q equals to 0, then pi equals to 0. So here equation number 2. From equation number 1 and 2, so here both are equate. E electric field E equals to 0. Okay, this is equation number 3. So field due to uniformly charged cell. So inside the spherical cell, the electric field intensity is 0 inside the spherical cell. So this is the electric fields and charges. Thank you.